meeting is being recorded.
And share my screen. Okay. I hope you are seeing my screen well and my slides. So in this session, in this following hour, I'm going to talk about a bit about POP. You heard mentioning it, and it's the project that is organizing this training together with the NCC. But what is POP, and also what is the methodology that we follow in the project? So POP is a center of excellence, and we focus on performance optimizations and productivity. And apart from that, we try to promote best practices in parallel programming in the European community using HPC resources. We do this by providing free services. So we provide these services to any user in Europe to understand the behavior of their application. And with these services, we suggest some improvements or optimizations to make their code more efficient. This is the transversal CoE. The other CoEs are usually focused in one science or field, or CoE is transversal in the sense that we cover all the application areas. So POP is now at its third edition. We started in 2015. The objective of the Center of Excellence is to perform the performance analysis and to develop a common methodology for performance analysis. So in the same sense as we have the programming models and operating systems that isolate the user from all the details of the hardware, in our Center of Excellence, we try to do the same for the performance analysis. So we try to isolate from all the differences in the hardware, in the programming models, and in the performance tools, the user, so that we have this common methodology. So as I said, this is the third edition of POP. We had POP 1, POP 2, and now we are in POP 3. POP 3 will end of this year, December 2026, but we still have time to do a lot of things. So don't hesitate to contact us if you want to collaborate. And we hope for a POP 4 edition that will start in January 27. So in POP, we have a diverse set of partners. These partners brings excellence in performance tools and in programming models and in performance analysis. Some of these partners bring their own tools. Some of these partners bring their experience in performance analysis in specific topics. We have experts in OpenMP, we have experts in vectorization, we have experts in MPI. And together we have all this expertise that we cover all the areas. But with this common methodology that I will share later on. So the objectives of POP can be divided in two. So on one hand, we have the assessment services that we provide, and on the other, we have the tools and the methodology that we developed in the project. But instead of seeing it like this, I prefer it to see it like this. So we develop these tools and methodology that we use in the performance services that we provide, and from the feedback that we get from these performance services, we improve this methodology and these tools. Because if we detect that we are missing features, if we need to cover more programming models, what is people using, then we make the tools and the methodology cover it. So this is how POP works together in a flow that never stops of improving the tools and methodology and providing these assessment services. So now we have the context, what is POP, what we do, and I will present now what are the assessment services that I'm talking about and give a bit more detail on what we do in these performance services. And then I will explain the methodology that we use, that is the common methodology that is agnostic to the tools and the platforms. And then in the 2 following days of the training, we will focus on the tools. So in this training, we will cover these 3 aspects. Today, I explained the services and the methodology. And in the following days, you will see more in detail how some of the tools of the project work. So the POP services. The services of POP can be classified in two. The performance assessment, that is the primary service. So every customer should start in the performance assessment service because it's where we get the overall overview of how the application is performing. Then after the performance assessment, you can get to a second level service. In the performance assessment, what you will get is a general idea of the main issues that your code can have in efficiency or scaling, and you will get also hints on how to improve that efficiency or scaling. Then the second level services are more specific services. Depending on what we have seen in the first service, in the first assessment, then we can say, okay, for your code is better to continue with this second level service. Who can apply to a POP assessment? Any user or developer in a European country can ask for an assessment. Or target are either code developers, so if you have your own code and you are developing it and you want to know how it, where you can improve it or optimize it or make it more efficient, but also users. Even if your code is not yours, if you are extensively using one code and you want to know if you are using it efficiently, which is the best configuration to run, then you can also apply. But we also work with the operators of Euro HPC systems and also with vendors. So the kind of insight that we get from the POP analysis can go to any of these actors. Or main customers are code developers and users of Euro HPC systems. So how does it work? We have an online form. You have here the link that you can check later, and the user or the developer can ask for an assessment in this form. You fill the form, we receive it in the project, we assign an analyst to this assessment depending on the answers from the form. So in the form, we will ask very basic questions, which is the programming model, which are the language, and if you have a feeling of which are the issues, in case you have any other comment. But if not, we will find them for you. And based on the answers on this form, we will assign the best analyst of the project to take care of that assessment. When the analyst is assigned, then he or she will contact the customer and they will decide the main details of the analysis. In which system do we want to do the assessment? Because this is important. If you usually run in one cluster or in one platform, the best thing is to do the assessment there, because at the end, the performance will also depend on the platform that you are using. And also the configuration will be the one that you are used to be running it. And so we will decide where the assessment will be done, and depending on where it is done, because if you have your own cluster and you prefer to do the assessment in your own cluster, then we can help you install the tools and everything to get the performance data, the traces or any performance data that we need in your system. And if you say, no, I usually run in Euro HPC systems, I request Euro HPC projects to run, so I prefer that POP does the tracing for us, then it's you that will help the analyst install your code in the selected system so that we can obtain there the performance data. One thing that is very important at this point is not only selecting the correct platform, the one that it's more useful for you, but also to select the most relevant use case to analyze. So it's better that you give us the production run that you usually use instead of just a dummy benchmark case, because we will always see more interesting things when analyzing a production run that it's interesting for you. When we have decided this, then as I said, it can be that the POP expert provides instructions on how to install the tools and obtain the traces. And from that, we get the traces. The POP analyst is the one that will be doing the analysis of these traces to get all the information and do the performance assessment. This performance assessment will finish with two things. On one hand, you will get a report summarizing everything that the analysts have seen, and also a call that will be a call between the analyst and the customer explaining the findings. At least there will be one call, but it's better if we have more than one during the process of the assessment, because you do the first call to try to decide which is the best configuration. But in the middle, it's good also to share what the initial findings, to see that we are aligned and that what we are finding out and what we are analyzing is relevant for you. But at least at the end, you get a final meeting where everything is explained to you, where you can ask all the questions, and you get all the information about your assessment. At this point, in this report, we can also discuss, or in this call, we can also discuss if there's relevance for a second level service. So based on what we have seen in the code on the interest of the user, we can decide to do a second level service. Then, which are the kinds of second level service that we offer? We offer a proof of concept. A proof of concept consists on a small modification. So usually in the context of POP, we don't do code modifications, we don't do code portings. All we do is performance analysis and then give hints and what happened? Okay.
Sorry, my bad. I think I misclicked actually. I didn't plan to do that. I'm very sorry.
Okay, no problem. I was saying, so the usually in POP we don't do code changes. So you analyze your code and we give you information and hints on how to optimize your code. But the proof of concept is an exception to this, is when we see that we can modify a small part of the code to show what we are saying in the report. So if in the report we say that if you change the way your communication is done, and we can change that easily in the code, then we can show you the potential of that change. So what we won't do is port the whole code or modify the whole code. But if we can do a small modification to show the potential of the optimization that we are suggesting, that's a proof of concept. That way you can see if the potential of our suggestion, and you can decide to implement it in the rest of the code to bring it up to the production runs. The advisory study, that is another kind of second level service, consists in kind of the other way. If if the user wants to do the changes that we suggested, but wants the analyst, the POP analyst, to accompany him or her during this process. So that way the customer will be the one doing the changes in the code, and we will keep analyzing them to see that they are going in the good direction. So in this case, the user is the one changing the code, and the POP analyst is helping see if the changes are going in the correct direction. The correctness check is a special one when we detect during the performance analysis that there can be some issues in the correctness of the code. In some cases, if they are severe, maybe we need to do the correctness check before the performance assessment, but usually we do first the performance assessment and then the correctness check. And then the energy efficiency is another kind of second level service where we analyze the energy consumed by the execution, and we check if there are parameters that can be changed to improve the energy efficiency of the execution. So these were the services that we provide. And as I said, we have a common methodology inside the project, because although we are a lot of different partners with different expertise and different tools, we have this common methodology. So in this presentation, I'm going to talk about the POP methodology. As I said, it's agnostic of the tools, but in my case, everything that is shared in the presentation will be based on the BSc tools because it's the ones that I'm more comfortable with, which are Extrae, Paraver, DMMAS, and the model factors. But the same things that I'm showing here in my presentation, you can do it with the other tools that we have in the project, and you will see it in the following days with the presentations about the tools. Also, in these presentations, I will focus on MPI applications. Why? To keep it simple. But the methodology of POP is extended and can be applied to hybrid models, MPI, MPI plus OpenMP, MPI plus GPUs. We can also use it to analyze I/O, vectorization. So we cover more areas, but today I will just to give you an overview of how we work, of the metrics that we have, and which is the process of the methodology. I will be only focusing on MPI applications, okay? So what is here, taking it from where Brian left it, what is a performance analysis? So for the performance analysis, I always say that we have these three actors. No? You have the user, and the user have a system where it is running, a code that it is running, and an input case that it is running. These are the three things that will affect or impact the analysis. From here, we get a trace, a radiography of what is going on really during the execution of your code. So it's not a simulation, it's really recording what is happening during your execution. With this you will get a trace, and this trace you can pass it through this methodology efficiency metrics that we have that will give us some metrics that will point to where the efficiency is being lost. So I usually say that this is going to the doctor, you get your analysis, and from the blood test, you see a set of numbers that will tell you where is the problem. But this is not the diagnostic, so the doctor does not diagnose you based on those numbers. After that, it needs to check more details. So when we have red numbers here, then is when we do a detailed analysis of the traces, and this will give us the diagnosis of your code. So this is important. This is the process. We get the traces, we get the metrics, and from the metrics is when we do the detailed analysis, and it's when we are able to provide this insight and this information on the issues of your code. So the process of the performance analysis that we do is we start identifying the structure, then we select the focus of analysis, so which part of the code we will focus on or analysis on. We obtain the efficiency metrics for this region, and depending on what the efficiency metrics tell us, we will analyze one thing or another, and then from this analysis, we get to the conclusions. So we start with identifying the structure. The idea of this, which may seem not relevant or very basic, is quite important. So it helps us understand the general structure, identify the different phases of the application, detect if there's an iterative pattern, the granularity of the code, and it can be easy or not that easy. So this is a Paraver trace, a trace visualized with Paraver. I will explain it as it's the first, maybe it's the first time that you see one. So in the x-axis, you have the time from the beginning of the execution until the end. And in the y-axis, you have the different threads that executed this application. Each row is one thread, and then the code color can mean different things. Depending on the window that you are looking at, the color can mean different things. In this case, in the top trace, what we are seeing is the MPI calls, code colored. So in the pink here, for example, it's an all reduce. And in the bottom trace, what you see is the useful duration, and this is coded in a gradient color. So from small durations that are green to long durations that are blue. So in the top trace, when it's black, it means that the code is executing. When it's in a color, it means that it's in MPI calls. In this window, in this execution, what we see is a clear pattern. We see that there's an initialization and then that there's an iterative phase. And that also from this iterative phase, what we see is that the iterations more or less look the same. So this means that we can select a few to analyze. So we don't need to analyze everything, as all the iterations more or less look the same. We can select a few of them. This is another example. We still have the MPI calls at the top and the useful duration at the bottom. And we can still see some pattern here. We see that there are 6 iterations. Although they don't look the same, they have different patterns of load imbalance and durations. And we see that there's a finalization phase that is different from the other. So we see the 6 iterations and the finalization. And then there's this other example. In this other example, it's almost impossible to see a pattern. There's no global synchronization that usually help us identify a pattern. If we zoom in, so we zoom here, we still don't see a clear pattern. So in this case, the structure is not that easy to determine. We don't see the clear iterations. So what I wanted to show is that it's not always that easy to find the pattern and to select what to analyze. And it's important to do this first step of seeing the global view, what I am looking at, which are the durations of different phases, how do they look like. Once we have seen this structure, then we say, okay, from this, what I want to analyze. And this is not a question that has a correct answer. This depends on what is your interest or the interest of the user or the customer. Because if I see this kind of execution, but I would, and without more information, I would say, okay, I will analyze 3 iterations from the iterative part because it's the most relevant one. But if the customer comes and says, I know very well how my iterative part works, but I'm worried about the performance of the initialization, because I know that in some use cases, the initialization is the bottleneck. Then we can focus and set the focus of analysis in the initialization. So the message is, this is a dialogue. If you say, I just come as a white canvas, tell me what you find, then we do our thing and try to find the best focus of analysis. But if the user comes with an idea or a region that they want to focus their analysis on, then we can select that as the focus of analysis and focus on our analysis there. In these cases, if we come without information from the user, what would I do? For the first case, I would select 3 iterations from the middle, not the first ones, not the last ones, because sometimes they have perturbations. 3 iterations because they are representative of most of the time. For the second one that had different patterns for the different iterations, I would select all the iterations because one of the iterations will not be representative of all the other ones. So in this case, I would probably select as the focus of analysis all the 6 iterations. And for the very complex one, we could select like the whole thing for the focus of analysis, but we could also focus in one small part to have the details on what's happening inside one of the nodes. Once we have selected our focus of analysis, we say, okay, now we are going to obtain the efficiency metrics for this focus of analysis. See that I say we will get the efficiency metrics for this focus of analysis because the efficiency metrics depend on in which part you're applying them. So you can apply the efficiency metrics to the whole run. You can apply it only to some iterations. You can apply it. And that's why it's important the focus of analysis, where I am applying these efficiency metrics, because I will get different values on where I apply them. So now we get the efficiency metrics. What are these efficiency metrics that I'm talking a lot about them? These efficiency metrics are some metrics that will tell us where the efficiency is being lost. So they are not so much a profiling metrics, how much time I'm spending in MPI, which is something that we could be more used to computing, but going one step further and giving you more information where the efficiency of your code is being lost. These metrics are a hierarchical model and they are multiplicative. This means that the product of the child will give the value of the parent. And we have two kinds of metrics. The ones that are colored in blue are the efficiency metrics that will give us absolute values on where the efficiency of your code is being lost. And the green ones are the scalability metrics. These are the metrics related to the computing part of the code. As we cannot say if this code is 10%, 80% efficient because we don't know the details of the hardware or how far this hardware can support your code, then these metrics are always compute based on a base case. So we have several runs. Then the first one will have 100% values in the green metrics, and then in the other ones will be compute based on this one. So these efficiency metrics are not the end of the journey. This is what I was telling you at the beginning. It's giving us only information on where to look next, or giving us warnings, a red light on where an issue in your code can be. They give us a general mechanism, a global overview of where the efficiency is being lost. It tells us where we want to look because it's where we can gain most. And it's a way of quantifying the efficiency loss. And it's also very good because it allows us to compare different code versions, different scaling, different codes, different architectures, different applications. So as we have the same metrics, we can apply it to different runs and allow us to compare. So now I'm going to talk about these metrics. And for each one of these metrics, I'm going to explain what it quantifies, how it is computed, and the interpretation, and what to look next. So once we see a low value in this metric, a warning in one of the metrics, what are the next steps that the analyst will do? But first, let me show you really how they look like. So when you get the efficiency metrics with one of our tools, because we have this automatized with some of our tools to get automatically these metrics, you will get something like this. It's a table where every row is one of the metrics that I was presenting before in the tree, and every column is a different run. In this case, and the most typical situation is where you have a scaling. So you run your code with a number of MPI runs, and then you scale it up and you scale it up, and you obtain the traces, the metrics for each one of the runs. And then you get this kind of table. We usually color code it so that it as a heat map, so that it helps us identify quickly which are the most relevant values. Okay, now we have the table. What do I look for? The first thing would be to look for the low values. Okay, these low values will give you the first thing to look at because it's where most efficiency is being lost. But also the trends. So in this case, for example, we see that the serialization efficiency, although it's not as low as the instruction scalability, it has a trend that it's going down. This means that maybe here is not so relevant for this scale, but maybe if we scale 1 or 2 steps more, it will be the bottleneck. So trends are also very important to see that there's a trend of one of the metrics going down. And also high values. In this case, for example, the computational scalability is going up, is going above 100%. How it can be that it's going above 100%? Well, because the computational scalability is the ones that I was telling you that is compute based on the base case. So you see here that we have the base case where the values are 100%, And then all these values are computed based on the base case. If we have high values in this, means that they are performing better than the base case. But what's happening here? So we have that the IPC is going up because the IPC scalability is going up, and this metric going up is hiding us that there's something going wrong in the parallel efficiency. So the parallel efficiency, if you see, is going down, is at the last not so good, with 75% of efficiency, but the global efficiency, so what you would see if you scale and you just check the speed up of your code, would be that it's not that bad. But in reality, it's being hidden by the fact that the IPC is going up. So this kind of relationship between the different metrics is also important to check. So it's not only one value. When we see this table, we need to see the global picture and to try to understand which are the things that are compensating and so on. So now let's start with the metrics. But first, to explain you how the metrics are computed, I need to give you some semantics. So we work with traces. If we have something like this that is representing a trace, you see that the blue is computing, red and the other colors are MPI calls, for example. Then from this trace, we simplify each process to have two states. The states can be either computing, which we call useful, or communicating. And then from this is from where we will compute all the metrics. So you have here all the definitions of the different things, the compute time of one process, the total compute time, the elapsed time, and the number of processes. This is all the definitions that we need for understanding the metrics that I'm going to explain now. So the parallel efficiency, this is the parent metric of the parallel efficiency. So we have the global efficiency, which is divided in parallel efficiency and computation scalability. The parent metric for parallel efficiency is telling us which part or which fraction of the of computational resources we are using to do useful work, and which part is being lost because I'm parallelizing my code, and then they cannot, that part of the computational resources cannot be used to do useful computation. So basically, if we have the two states that I explained before, the parallel efficiency is how much compute time, so the sum of all the compute time of the execution, divided by the total time, so the total area of time that I was using, which will be the number of processes multiplied by the elapsed time. So this is giving us how much time of the whole time that I'm using the resources, I'm using it for doing useful computation. The interpretation is that your parallelization is making it not be quite optimal. And I would look, what you will look next, at the child metric. So in this case, as a parallel efficiency have two child metrics, I would look at which one of these two child metrics is the one that is having a lower value. So in this case, the child metrics of the parallel efficiency is the load balance and the communication efficiency. So what is the load balance? The load balance is the time that is being lost because one process has more work than the others. And how do I compute this? I usually see it as collapsing the computation. So we have here the original trace with the useful and the communicating. And then I collapse all the blues to the right, to the left. And I get something like this. So we say, okay, because this process here has more work than the others, all this time that is marked in yellow is being lost. Then this is the time that we consider as load imbalance. And we compute it like that. all the blue that is inside here divided by the maximum process that was computing multiplied by the number of processes. So you have the formula here. You have to take into account that this load balance metric that we are using, it's giving us an idea of the global load balance. So because it's accumulating. So if you have different imbalances in different parts of the code, this will be hidden and will be shown in another metric. This metric also has the property that is telling us the time that is you are losing due to that. So this means that the load imbalance that you will get from a situation like this compared to a situation like this, that you could think that it's similar. So there's one process that has twice the work than the others. And in the bottom example, there's one process that has half of the work than the others. It seems to be a similar situation, but in reality, the amount of compute time that you are losing due to this imbalance is very different. In this case, you are losing all this area here, while in this case, you are only using this row here. And if you compute the load balance for this situation and the load balance for this situation, you will get this number. In the top one, the load balance is 0.6, while in the bottom situation, the load balance is 0.1. So this is the message. It's giving you, this metric is giving you the idea of the time that is being lost due to this person having, or this process having more work than the others. Okay, I have a low value in load balance. What do I check? Well, to understand the issue of load imbalance, we go to the fact that the compute time is composed by three factors: the number of instructions, the IPC, the instructions per cycle that I'm able to execute, and the frequency at which I'm executing those instructions. So this is the three things that we would check to try to understand where this load imbalance is coming from. So we can be that the number of instructions has load imbalance, that this is something that we can see in this plot here from Paraver. This is a histogram, and this is, for example, and this is telling us how many instructions each one of the processes, again, rows are processes, are executing. We see here clearly that there are three processes that are executing more instructions than the others, for this burst, and for these ones, and for these ones. So in this case, for example, we would say, okay, the problem with load imbalance are instructions. What if the problem of imbalance does not come from instructions? Coming from instructions means that they have more work to do. So for some reason, for the partition or whatever, one process has more work to do than others. If this is not the case, then we can check the IPC. In the second trace, here we are seeing the IPC. We see that there are some processes that has a different IPC than the others. Then I would check the histogram of IPC to see where the difference is. And if it's not the number of instructions or the IPC, I would check the frequency. So these are the three things that will give us the idea of where the load imbalance issue is coming from. Is because the work is not distributed evenly, or because some processes are slower in executing that. And it can be because of some NUMA effects, in the case, for example, of IPC, or it can be in some hardware heterogeneities, in the case of frequency. Okay, the next metric, the communication efficiency. What is telling us the communication efficiency? The communication efficiency is telling us how much time I'm losing because the communications are not instantaneous. And communications are not instantaneous for two reasons. One is because I need to wait for somebody to communicate with them. And the other is because data is not instantaneously transferred from one point to another. So for computing the communication efficiency, we we computed before the load balance as the yellow parts, the communication efficiency is what is left. So the time that I'm losing, even though if all my processes were computing the same time. So this is how we computed the blue plus the yellow divided by the whole rectangle. So how much time the most loaded process was computing divided by the total time. And what to look next if we see a load value in the communication efficiency. As communication efficiency have two childs, serialization and transfer, we could check the childs. But in some cases, it's not possible to get this child. So if I'm not able to check the child metrics, then I would check how many MPI calls are made, which is the histogram of MPI calls. How often, which are the granularity of the computations. I'm communicating a lot with very small messages, like for example, in this situation, I see the useful duration and I see that it's very small. So it means that I'm communicating very often. Or I'm sending a lot of data. In this case, for example, I'm checking all the data that is being sent between two processes. So which is the amount of data that is being sent. And also the semantics of the communication, which is the pattern, what is happening. So are dependencies between the communications between the processes. So in this case, for example, we saw that there was an application that started well aligned, and then for some reason, this chain of dependencies made this skew in the pattern, and this was because these processes had one more communication than the other, so it took longer, and then these ones were waiting for this one, so they took longer, and then these ones, and then you end up with this skew pattern. So checking also the semantics, who is communicating with who, and which pattern in the communication do I see. If I'm able to get the child metrics of the communication efficiency, which are serialization and transfer, what do I see? To compute the serialization and transfer, we, in particular now the transfer, that is the one that I'm talking about, we need to know what would happen if this was executed in an ideal situation. So we do this using a simulation. We simulate what would happen if the communications were instantaneous when sending the data. So I still need to wait for the other process to be available to receive or to be to reach the blocking call. But the moment both processes are there, or all the processes involved in the communications are there, the data transfer is instantaneous. And I get this. This is a simulated trace of the previous one, where you see that the time that all of them were in communication is collapsed. So this gives us that this time would be gained if the communications are instantaneous. So the transfer time is telling us the time that is being lost, or the efficiency that is being lost, because communications and data are not moved instantaneously. Be careful, because it's not only about network. So this metric is also talking about overheads of MPI, for example. So if you do a lot of small communications, you will still see an overhead that is being paid as latency, and it will still be a transfer efficiency. And we compute it by the ratio of the total time that we had compared to the ideal time of this execution, where the communications were instantaneous. What do we look when we see this transfer efficiency? Well, the question that we try to ask is it a problem of overheads? Is it a problem of latency of the network? Or is it a problem of bandwidth of the network? For this, it helps a lot, these simulations. We have one of the tools that allows us to do this kind of simulations and change the parameters of the simulations. So something that we do is, okay, this is the regular run, the one that we got, and this is the ideal one. And what happens when I run with a very low latency? and a nominal bandwidth. And what happens when I run the other way with the very low bandwidth and a nominal latency? Comparing these traces and comparing these simulations allow us to see what is impacting more the execution. Is it the bandwidth? Is it the latency? Or is it the overhead of MPI? And the last of the parallel efficiency metrics is the serialization. So what is serialization? It's what is left is when the different processes are waiting for each other. When I have different chains of dependencies, different patterns of load imbalance. How do I compute them? So we said, okay, we have the ideal runtime. We had collapsed the computations to compute the load imbalance. And then what is left here is the serialization, is the time that the processes are waiting for each other. And it's computed as the maximum, the process that has more compute time divided by the ideal time that would be here. This metric is one of the most difficult ones to analyze from my point of view, because it can have a lot of different sources, because it can be noise. For example, one of the things that I would discard is noise. It can be micro imbalances, so load balance patterns that are different in different phases of the application and don't appear in the load balance metric, appear here in the serialization. It can be chains of dependencies between different processes. It can be actual serializations. So the serialization efficiency can have a lot of different causes, and what I would try is to discard noise, check that the cycles per microsecond do not change. Try to identify if there are circular waits. So now I wait for you, then you wait for me. This will create a serialization, and understand. It's very important to understand the semantics of the communication. Then check the MPI calls, and as I was saying before, check these kind of patterns where ones are waiting for the others, and this is creating these dependencies and this inefficiency in the communication. Okay, so we have gone through all the parallel efficiency metrics. How they were computed, and what I would analyze afterwards. For the computational scalability metrics, is a bit different because, as I said, they are based in a base case. So they can be computed both if we are doing weak or strong scaling. They are computed slightly different, but they mean the same, and they can be computed. And what we do with composing three child metrics, because we consider that the execution time is the number of instructions divided by the IPC multiplied by the frequency. So the computational scalability is computed based on the execution time, the useful time of the base case, compared with the useful computation time of the current run. And the formula to compute it is just the ratio between the two of them. Then the instruction scalability is computed an analogous way. So we have the reference and the current number of instructions. We compute the total number of instructions in useful. This is very important. So we divide parallel efficiency, the time that is not being used doing useful computing, computational scalability, the time that is in useful computing. So this means that all the metrics here inside the computational scalability is in useful. So these are the useful instructions divided by the current useful instructions. The same for IPC, but the formula is reversed because the IPC was in the denominator. So the current IPC divided by the reference IPC. And if I have a value above 100%, indicates that the IPC is increasing as I scale up. This is something that can happen when you have catch effects that the problem size is getting smaller as you scale, and then it fits better in the cache. So you will get an IPC higher when you scale up. And then the frequency scalability. The frequency scalability, this is a metric that for us is very clear. For the user, sometimes is a bit confusing because the frequency scalability is from the point of view of the process. So the frequency scalability can be affected by the frequency of the process, of the processor. If we have a DBFS scaling, then the frequency scalability will change. We will see a difference in the frequency that is measured for that process, but also can be affected by other factors that are not hardware. So if the operating system decides to preempt this process and take it out of the CPU to execute something else, we will see a decrease in the frequency. If the process is doing a lot of I/O, then the frequency is also reduced. So it's not only the frequency of the scalability. Sometimes in this metric, we see other factors that it's not only hardware and that can affect the metric. So the idea is from all these metrics, then you can do the detailed analysis. From this detailed analysis, we present the conclusions and suggestions on how the code can be improved or optimized. This is important to notice that these are the metrics that I have been talking about, but then the causes for these metrics are diverse and they are not one-to-one. So we have that, for example, the IPC scalability can be affected by the numinous, but also by the sharing effects of memory bandwidth, for example, but also that the operating system noise can show in load imbalance, in serialization, in transfer, or in frequency scalability. So this is why we say the metrics are not the final diagnosis. The detailed analysis is what will bring us from the metrics to the real cause. So when we do the analysis is when we are able to really check which one of these causes is affecting our code, and then give really a hint or suggestion to improve the code. So after almost an hour talking, what I would like you to keep from this presentation, from these 50 slides. So we have POP services. They are free. They are available for all European users. You can request your performance service in this form. You can contact us if you have questions, if you are not sure if you can apply to it or if it can be useful for you. You just can send an email and we can discuss the details of your service. POP methodology is agnostic to the tools, agnostic to the hardware, agnostic to the science, to the code, and it will give us a global overview of what's going on. And most importantly, it gives us hints on the main efficiency bottlenecks and where to look. The methodology covers MPI, OpenMP, hybrid, MPI plus, GPUs, vectorization. So it covers a lot of things, although the presentation of today was only focused on the MPI codes. And we have a set of tools that allows us to follow this methodology, both to get the metrics and do the detailed analysis. They will be covered in the following days, and they are available to the users. All of the tools that will be presented the following days are free and online, available for you to test them. And they are also installed in all the Euro HPC systems because we have been deploying them, and they should be available in all the systems. And regarding these trainings, as Brian was saying, we also do advanced training. So if you finish this training that we are doing these 3 days and you feel that you want to know more about the tools or about the methodology, you can follow us, and we will do more trainings, more in depth in some of the functionalities of the tools, and covering more tools, because in these 3 days we will cover a small set or a very basic set of the tools that we have in the project. And that's it from my side. I will stop. I cannot stop. Nothing now. Oops. Brian, can you stop the recording? Because I lost the controls.
Not sure that I'm in charge, but stop. No, I can only stop video.
Maybe you can stop sharing, Martha. This will help you.
No, I
actually.
can't. I lost all my controls, so I can't do anything.
Okay.
I lost the Zoom control now, so I don't know if I can.
Maybe let me try to stop your sharing. Maybe
Yes,
that will help.
please. No, thank you. Okay.